Okay, guys. So yesterday we learned about how to solve problems using momentum, this idea of m times v, the momentum. And we learned how to solve problems in a very limited way because all the examples that we worked with yesterday were what we call one-dimensional problems, problems where the objects in question were only ever moving in a single direction, left or right or up or down, but there wasn't anything more complex where maybe objects were moving in weird diagonal directions. And the reason that's important is because momentum is a vector and the direction matters. And as long as things are one dimensional, you can keep track of the direction with pluses and minuses, positive and negative, left and right. But the minute you open things up to more complex interactions, you're going to have to use full-on vector notation to deal with situations of that nature. And so my goal here today, and I suspect this is going to be a fairly short lecture, comparatively anyway, is that we're going to deal with uh, solving problems using momentum, but we'll be doing it in two dimensions at the same time. And all we're going to have to do is bring to bear what we learned about vectors back in chapter 3 and apply it to what we're doing now. And I think the easiest way to handle this is just to dive in and to do an example problem, because there's really not a new concept to learn. It's just we're applying concepts to a more complicated situation. So let's start with this. I don't know if you've ever been around like a traffic accident that has occurred and seen either like the police people that are responding to the scene or sometimes the insurance guys. They're at the scene of the accident, and often they have that little, like, it's like a stick with a wheel at the bottom, and they're rolling it along the tire tracks at the accident site. And the reason they're doing that is because that little wheel with the stick is really a kind of tape measure, right? And as you roll the little wheel across the ground, the more the wheel rotates, the further distance it's traveled. And they're able to measure the distance that, say, a car moved while it was skidding uh, in order to figure something out. And what they're doing with that is we learned back in chapter 2 how to solve for, say, uh, the kinematic variables of an object. And the idea is if you've got a car and that car begins to skid, it leaves little skid marks on the ground. And you can measure those skid marks, and that's going to tell you the displacement that they had while they were skidding. Um, if you know this distance and you know things like the coefficient of friction between a typical tire and the road, you can often use the coefficient of friction to figure out what the acceleration of the car has to be. So if you think about this in terms of one-dimensional kinematics, uh, the tape measurements can tell you this and this. It stops, so obviously you know the final velocity. The acceleration you can get if you understand enough about how friction works on tires, so that's a thing you can know. So just in terms of things you can measure at the site, you could know everything except for V initial and T. And if you cared about V initial, you could use the stopping distance equation. And you could use that to solve for V initial. Why might I care? Well, maybe there was a car accident, and by measuring the skid marks, I can figure out how fast the person was traveling when they first hit the brakes. And then I know whether they were speeding and whether perhaps they were at fault for the accident and that kind of thing. So that's a thing you could certainly do. And I want to apply that basic idea. So let's imagine that there's been a wreck at an intersection between two cars. And what's happened is here's car one, and car one, let's say, is pretty heavy. It's 1,500 kilograms, and it's traveling in a four-way intersection. It's traveling with an unknown speed to the right. Now, meanwhile, heading into the same intersection is a second car, This car is a smaller car. Maybe this is an SUV and this is more like a sedan or something. Let's say that it's only 1,000 kilograms, which is still pretty heavy, actually. And it's traveling with some initial velocity in the other direction. Now, what's going to happen is they wreck. They crash into each other. And for simplicity's sake, let's assume that when they crash into each other, they both kind of get locked together and form one big nasty ball of wreckage. And that big nasty ball of wreckage ends up dragging itself and scooting diagonally, let's say at a 60-degree angle. And what's going to happen is the investigators come out and they're going to measure the length of the skid marks in this direction. And from those skid marks, they'll go through this process, and they're able to figure out that after the two cars hit one another, they're traveling with a speed after that collision of, let's say, 10 meters per second. Right? Or at least that's the speed they had immediately after the wreck based on how far they skidded after the wreck. Now, based on that information, what I would like to deduce is how fast must these two cars have been traveling before the collision? That's going to help me assess blame for the accident, right? And the cool thing is that I'm going to have enough information based on what I can deduce from the final velocity about how fast they must have been going before the collision, because I know that during the collision, momentum had to have been conserved. So that's our goal. We're going to use momentum conservation and solve for the starting velocities of each of those two objects. Well, I know how to find momentum. Hold that thought. I have a thing in the oven that just got done. I need to pull that out and pause the recording for a moment, or not. So we're going to use that to figure out what the speeds were before the collision. So I know how to find momentum, right? Before the collision, the momentum of this car, which I could call P1 initial, would just be equal to the mass of the car, mass 1, times whatever starting speed it has. And I don't know what that speed is, so I'm just going to call it V1 initial. And normally I would just do m times v, but that's the magnitude of my total momentum before the collision. I need to break that down into vector components. That's easily enough done because this is in the x direction, and let's go ahead and choose a regular boring coordinate system where the x direction is positive to the right and the y direction is positive upward. And since this guy here is traveling sideways, not up and down, he's got to have a momentum in the x direction, but nothing in the y direction. So it'll be this, whatever that is, in the I hat direction, but 0 in the j hat direction. Piece of cake. Now, what about car number 2 before the collision? So P2 initial. Well, his momentum is going to be, again, his mass times his starting velocity. However, it's traveling in the y direction, not the x direction. So the x component is 0, and the y component will be m2 v2 initial in the j hat direction. That's easily enough done. Now, after the collision, both of my objects have collided and locked bumpers, and now they're like one big moving ball of wreckage that's traveling together. So I'm just going to do P final for both of them. And of course, the magnitude of that momentum is going to be the mass of everything, which in this case is m1 plus m2, times the velocity of everything, which is v final, which we know to be in the problem 10. However, this is the magnitude of the total. I need to break that down into x and y components. And this is a diagonal. So it's going to have an x part and a y part, which I can get those parts using SOHCAHTOA. And I know that the x component is the adjacent part because it's adjacent to that 60-degree angle. So that I'll get by taking the magnitude times the cosine of 60. That's the I hat part. And the j hat part is going to be the same thing. Times the sine of 60 degrees. So how do I make use of this stuff? Well, I've taken my momentums before and after, and I broke them into components. And what I know is the big core concept for this entire chapter is that the momentum before has to equal the momentum after. Now, before the collision, remember I have to, this is really, I guess, a sum. So I should write the sum. So if I add up all the momentum before, well, that's this and this, right? But I'm adding vectors, and when you add vectors, you have to add them component by component. So I'm going to do this twice, once for the x direction and once for the y direction. So before the collision, I have in the x direction this and this. These are my befores. So the left-hand side of my equation is going to be these things together. So one of my equations will be m1 v1 initial plus 0. That has to equal my momentum in the x direction after. So again, here's P final. In the x direction, I have just this. But what about the y direction? In the y direction, before the collision, that's again, I'm looking at these two, I have this plus this. So M2, V2 initial. And after the collision, I have just this. So what I end up with are two equations and two unknowns. What are my unknowns? Well, in this case, I'm solving for this and for this. Now, the good news for us is that this is really easy because for this particular problem, this first equation only has one unknown in it. All I've got to do is get V1 initial by itself, and doing that is super easy. I just divide by M1. So for that one, the starting velocity for the first car is going to equal M1 plus M2 times V final times the cosine of 60 divided by M1. And when I plug my numbers in, we know that M1 is 1,500 and M2 is 1,000. So this is 2,500 times 10, that's 25,000, times the cosine of 60. The cosine of 60 should be the square root of 3 over 2. I'm not. Would you like one? Sure. Are you sure?
Okay, sorry.
Sorry. The cosine of 60 is 1/2, and I do that because I'm not stupid. So 25,000 times a half is 12,500, and 12,500 divided by 1,500. Oh, I'm having calculator errors today. Good grief. Is 8.33. So we now know the speed of the SUV prior to the collision was 8.33 meters per second. Neat. Now, what about V2 initial? Well, I'll get that the exact same way. You'll notice V2 initial is the only thing that doesn't appear or that appears in here that I don't know. I'll just divide both sides by M2. And so that's going to equal M1 plus M2 times V final times the sine of 60 divided by M2. So the sine of 60 is going to be the square root of 3 over 2. And it turns out that this guy here is traveling at a whopping 21.6 meters per second. Right. That's just under 50 miles an hour. So at a four-way stop, maybe you shouldn't go through the four-way stop at 50 miles an hour. So who's getting a ticket? This guy. How do we know that? Because the trajectory of the two objects after the collision solely depended on its y component of the momentum from this guy. So by knowing how much y momentum we had in my final answer, we could deduce how much y momentum I must have started at with the original car. All right, so super easy, piece of cake. Now, this particular example was really straightforward mathematically, simply because when I solved this problem, I only had one unknown in each equation. It could, of course, get more complicated. How would it get more complicated? Well, let's change the scenario slightly. All right. So if you've ever played pool, sometimes you have to make shots that are a little bit tricky. For instance, imagine that I've got the ball that I'm trying to sink right here, and the pocket that I'm trying to sink it in is right over here. However, the cue ball that I have to hit it with is over here. Now, in order for me to get this ball to go into that pocket, maybe I estimate that I'm going to have to shoot it in this direction. And maybe in order to get it to go far enough, maybe I've got to have it start by going a speed of, let's say, 5 meters per second. And I've got to go at, let's say, a 45-degree angle with respect to the horizontal. Now, meanwhile, in order to make that happen, I can't just shoot the ball straight at it, because then this ball will go straight away and I'll miss it. So what I end up doing is I'm going to hit these two objects slightly off center. We say that it has an impact parameter that is non-zero. So I'm just going to kind of go up there and just barely kiss it and have it bounce out that way. And I could certainly pull that shot off, but part of playing pool isn't just about getting the ball to go where you want it to go. It's also about making sure that you know where the cue ball is going to end up after your shot, because you want to make sure that you set up your next shot, or you want to make sure that you don't accidentally sink the cue ball in the process and lose the game because of it. So I want to figure out, after I hit this thing just right to make this thing go into the pocket, where do I expect this cue ball to end up? And what's going to happen is, when I hit, if this guy is going to go bouncing this way, he's going to have a little bit of momentum in the y direction. And the only way that I can test for it, if this guy is going to shoot with some initial velocity that is horizontal, that implies that my cue ball after, so this is ball 1, this is ball 2. So ball 1 after the collision, I suspect, is going to go bouncing off down here, but I'm not really sure what velocity it's going to have, nor am I completely sure what angle it's going to go rushing off at. From common sense, I can kind of guess that it's going to go down into the right, but I can't be sure. So that's my goal. My goal is to figure out, where is that cue ball going to end up? What velocity is it going to have? What direction is it going to travel? Assuming that I hit the two ball in the correct direction. Now, this is still going to be a momentum conservation problem, because during the collision, when ball 1 hits ball 2, there's going to be momentum conserved. And we'll approach it the same way we've done previously. Let's choose a boring normal coordinate system. So there's the x direction. There's the y direction. And let's break down my momentums before and after the collision. So let's start with ball 1 before the collision. So P1 initial. Now, the momentum of the one ball before the collision is going to be its mass 1, times V1 initial. And In this particular problem, it's traveling sideways, but not up and down. So all of that's going to be in the x direction. None of that is going to be in the y direction. Now, what about object 2 before the collision? Well, in this case, the ball that we're trying to sink, it's not a moving target. That's not how pool works, right? The ball is just sitting there waiting to get hit until I hit it. So how much momentum does it have before the collision? None. 0 in the I hat direction and also 0 in the J hat direction. It's just sitting there waiting to get hit until the other ball strikes it. Now, all bets are off once the hit happens, because now what's going to happen is P1 final, that's going to be this guy here. And notice, I expect it's traveling in the x direction, but probably the negative y direction. I'm going to take that into account just to make my life easier. So the total momentum of this thing is going to be whatever its mass is times whatever its final velocity is, so V1 final, and we don't know this, we're trying to solve for this. And that's going to have components in the x and the y direction. The x side is the adjacent side of the triangle. So that'll be times the cosine of whatever the heck that angle is that it goes zooming off at. And I don't know what it is. Meanwhile, the y component I would get from the sine, so it's going to be minus m1 v1 final times the sine of whatever heck that angle is. And hopefully you guys are to the point where you can see where this is coming from, because again, we break down vectors into components a lot. So hopefully you're getting good at it by now. So this is the momentum of the cue ball after the collision. To do the other guy, its momentum is going to be its mass, mass 2, times whatever the heck V2 final is. And again, I can break it into x and y components. So that'll be times the cosine of 45 for the I hat part. And of course, for the J hat part, it's upward, so it's plus M2 V2 final sine of 45. So again, I've taken the momentum of both balls before and after, and I've broken them down into their x and y components, because I know that momentum is conserved, so the total momentum before the collision should equal the total momentum after the collision. And I'm going to have to do it in each direction, once for x and once for y. That's going to give me 2 equations. In the x direction, the sum of the momentums before is going to be these 2 things right here. So I'll have m1 times v1 initial. That's going to have to equal the sum of the momentums in the x direction afterward. That's going to be this and this, because they're both I hats. So that's going to be one equation that's going to have to be true for this particular scenario. Now, what about the other direction? Well, in the y direction, before the collision, I literally had 0 momentum in both directions. In the y direction after the collision, I'm going to have this, but it's negative, this, but it's positive. I'm going to write this one first because I like to write something minus something rather than negative something plus something. It just looks better. So M2 V2 final sine of 45 minus M1 V1 final sine of whatever the heck theta is. And so now I have 2 equations and 2 unknowns. What are my 2 unknowns? Well, in the problem, I know that V1 final, or sorry, V2 final is 5. That was given. But V1 final is whatever this is. So this is an unknown, and it appears there and there. Meanwhile, the angle that this guy's shooting off with is also unknown, which appears here and here. And you'll notice that for this problem, unlike the previous problem where each equation only had one unknown in it, in this equation, both unknowns appear in both equations. So in order for me to solve this problem, I'm going to have to use both equations simultaneously. Now, how do you pull that off? How do you solve two systems of simultaneous equations? Well, you pick one of your equations, and it doesn't matter which one you pick, but I will invariably start with the simpler of the two, which is probably the second one. And I'll pick one of my unknowns, and it, again, doesn't matter which one, although the algebra is going to be a little bit easier if I pick V1 final rather than theta, just because I don't have to deal with inverse trig functions yet. So pick an equation, pick an unknown, and get that unknown by itself. So I'm going to take this equation and solve it for V1 final. Now, in order to do that, I'm going to do two things. First, since this is negative, I'm going to add this entire term to both sides. So this is going to move to the other side. So I'm going to have M1 V1 final times the sine of theta, and that's going to equal M2 times V2 final times the sine of 45. Now what I'll do is, to get this by itself, I'll divide both sides by M1 sine theta. That's going to leave V1 final by itself on the left-hand side. And on the right-hand side, I'm going to have M2 V2 final times the sine of 45 all over M1 times the sine of whatever the heck theta is. Piece of cake. Now, if that's V1 final, I can take this expression for V1 final, and I'll go back to the other equation, the one that I haven't used yet. And I'll replace V1 final in that equation with that expression. So for that equation, I'll have M1 V1 initial equals, and I'm going to have M1 times V1 final, which is all this, M2 V2 final sine 45 over M1 sine of theta. So that times the cosine of theta plus M2 V2 final. Hold that thought. Yes.
Can you explain what that VF means?
What VF means?
Yeah, what does that mean?
It's V1 final.
Okay.
Yeah. So again, just the notation here, just make sure that's clear, is we have two objects, right? Object 1 and object 2. And V1 initial, like V1 initial, is going to be the velocity of object 1 before they crash into each other. V1 final is the velocity of object 1 after they crashed into each other.
Okay.
Does that make sense?
Yes.
Awesome. So yeah, it's not if, it's 1F. So that's my goal. Now notice, once I've made that substitution, the only thing in this equation that I don't already have a number for are the thetas. Jasmine, what's your question?
Is this second equation the first one that we did?
This one right here?
Yeah.
Yeah, what this equation is we took this equation and solved it for V1F, and then we plugged that value in here. So I just took this and rewrote it, but I replaced the V1F with all this stuff.
Okay, thank you.
Yeah, you're welcome. So now it's just a matter of doing some algebra, because the only thing I don't know in here is the thetas. Everything else is a number. Now, one thing I notice immediately is that mass 1 over mass 1, that right there is going to cancel anyway, right? The other thing I notice is that I have the cosine of theta over the sine of theta. And I remember from pre-calc class that sine over cosine is the tangent, right? So I can combine these two things into a tangent, except it's not sine over cosine, it's the other way around. So it's the tangent, but it's the reciprocal of the tangent. So what I can do is I can replace this term by putting the tangent on the denominator, right? If it had been sine up top and cosine on the bottom, I would have put the tangent up here. But because it's cosine over sine, it's like dividing by the tangent, not multiplying by the tangent. And of course, what's cool about this is that, again, tangent is the only thing I don't have a number for. Everything else is a number that I can plug in. So what I'll do is I'll get all the number junk on one side of the equal sign, and I'll get the tangent by itself. So I'll leave this alone for a second. I got to get rid of this first. Let's subtract this from both sides. So I have M1 V1 initial minus M2 V2 final cosine 45 equals M2 V2 final times the sine of 45 divided by the tangent of theta. Now, I still have a problem because the thing that I'm solving for is down here in the denominator. So what I want to do is get it out of the denominator. And the way I would do that is multiply both sides by the tangent. Now, if I did that, what I'd end up with is all this stuff times tangent equals this stuff, right? Except once I end up with tangent times all this stuff, I'm going to want to get this stuff out of there by dividing. And so just to keep the amount of space I keep on the page reduced, what I know is going to end up happening is this is going to swap places with all of this. So I'll end up with the tangent of theta equaling this divided by all of that. So, super easy. Now all I got to do is plug in my numbers. Now, one thing I don't know off the top of my head is what's the mass of a billiard ball? I don't know. However, I can make my life a little bit easier by recognizing the fact that for billiard balls, they all kind of look the same. The masses are all going to be the same thing. So even though I have M2 and M1 here, M2 and M1 are the same thing. And because M2 appears or M1 appears in every term, as long as they're all the same, they'll cancel. Now, if they weren't the same, I'd have to plug in my numbers and I'd get a different answer. But here, all these M's are going to end up not mattering because they're all the same mass. And it doesn't even matter what the mass is. The fact that they're the same means they're going to cancel. So now I'm ready to go. V2 final. Well, V2 final was the final velocity of object 2, which going back to the original object, there's object 2, its final velocity was 5. Ha! So that is 5. V1 initial, oh, I have to specify that. Well, let's say that I'm going to hit that cue ball at a speed of, let's say, 8 meters per second. So that's how hard I'm hitting it. I can pick how hard I hit. So V1 initial, we'll say, is 8. And then, of course, V2 final is still 5. So now I can figure out the tangent of theta. So up top, we're going to have 5 times the sine of 45, which is about 3.53. We're going to divide that by, on the bottom, it's going to be 8 minus 5 times cosine 45. So I get, for this entire fraction, I get about 0.719. Or sorry, 791. I'm becoming dyslexic in my old age. Geez. Let's carry out one extra sig fig there. Now, if that's the tangent of theta equals this, then theta should equal the inverse tangent of that. And the inverse tangent of 0.7919 is about 38.37 degrees. So now I know what direction the cue ball is going to bounce off. It's going to go off at a 37-degree angle. Now, I also would like to know how far it's going to travel, which means I need to know what speed it's going to go zooming off with. So I need to find V1 final. Fortunately for us, we've already solved for it because look, along the way, we had already found that V1 final equals all this garbage. So all I'm going to have to do is plug into there. Notice, by the way, that because the m's are the same, when I go to evaluate it, those m's are going to cancel anyway. And so that's going to be V2 final, which is 5 times the sine of 45 divided by the sine of 38.37. So my cue ball is going to go flying away at 5 point, we'll call it 69 meters per second. So now I know both the magnitude and the direction of my final velocity. And all I had to do was solve this momentum conservation equation. Boy, was that fun. So let me pose a question to the two of you who are actually here. Yesterday, we talked about elastic and inelastic collisions. What was the difference?
The difference was, oh, sorry, I have it in my book. The difference was one, elastic was momentum and energy are both conserved, and inelastic was momentum is conserved, but the energy is not.
So, of those two, which of those two would I expect this collision here is going to be?
Would it be inelastic?
How would you know?
Well, I'm just thinking about, okay, so I just think about when like the balls hit each other, like the momentum like is there to hit each other, but you know, eventually they stop rolling like on that. So I guess that's why I think that.
So that's good. It's good thinking that way. They do eventually stop rolling. However, I'll point out that the reason they eventually stop rolling is because they're skidding across the felt of the table, and the friction is what's causing them to stop. Now, the collision itself happens at an instant, and during that instant, the balls don't travel very far, so they don't have a lot of work done by friction, which is why we're able to use momentum conservation anyway. We can ignore the table as long as it's over that brief window of time. But after they've dragged away for a little bit, then we'd have to take into effect that it's a non-isolated system and the friction is bleeding energy away. But that's a different question. So it's good that you're thinking along those lines, but that's not going to help us because even if it was elastic or inelastic, they would still eventually fall. They would still eventually stop rolling because of the frictional forces as they move around. So it's something else. The way we're going to figure out whether something is elastic or inelastic is by looking to see whether the energy is conserved, right? We know the momentum was conserved because this whole process, we assumed it was, right? We assumed momentum was conserved, and that's where we got these values. But to know whether the kinetic energy was conserved, we'll figure out what was the kinetic energy we had before, and what's the kinetic energy we have at the end, and see whether or not those things are the same. So let's do that math. So kinetic energy is 1/2 mv squared, right? Now, for this problem, prior to the collision, how much kinetic energy did we have? Well, this ball here is moving, so it's going to have some kinetic energy, but this guy here was sitting still. He had none. So the only kinetic energy that we had at the beginning of this problem would be 1/2 times the mass of whatever the ball was, which again, we don't know the number for that, times the starting speed of 8 squared. So 8 squared is 64 times 1/2. It's 32 times whatever the heck the mass is. This is a number we can plug in later, doesn't matter. So that's my starting kinetic energy, 32 times whatever m is. What about my final kinetic energy? Well, after the collision, both objects are moving, so they're both going to have some kinetic energy. I'll have to just figure them out separately. Now, I know that this guy is moving at a speed of 5. This guy is moving at a speed of, what did we get for our answer? 5.69? So how much kinetic energy is that going to be? Well, K final is going to be the kinetic energy of ball number 1, which is 1/2 times whatever the mass is, times 5.69 squared, plus the kinetic energy of ball number 2, which is 1/2 times whatever the mass is, times his ending speed, which was 5 squared. Let's just work it out and see what we get. So this one over here is easy. 5 squared is 25 times 1/2 is 12.5. So that's 12.5 m. This over here is going to be pretty doggone close. So if I take 5.69 and I square that, that's 32.3 times 1/2 is 16.18 times whatever the mass is. If I add this plus this, so that plus 12.5 is 28.6 times whatever the mass is. So we started with 32 times whatever m was as our kinetic energy. We ended up with 28.6 times whatever m was for our kinetic energy. So having done that calculation, what's the answer? Is this elastic or inelastic?
Elastic?
Well, if it was elastic, what has to be true?
Both momentum and energy. So it's inelastic.
Yes. So how do I know it's inelastic? I solved the problem using momentum conservation because I know that's going to be conserved no matter what. But then after I figured out the velocities, then I just looked to see how much energy I had before and to see whether or not it was the same as the energy I had at the end. It wasn't, so it was inelastic. Had I gotten 32m, the answer would have been elastic. That's it. And if I'd gotten something more than 32m, then what that is something kind of unrealistic. That's like if I hit a billiard ball and one of the balls explodes and generates internal energy that wasn't there before. So usually, if the problem is realistic, the final energy won't be bigger than the starting energy. In order for that to happen, the something would have to provide its own power, and that's probably beyond the scope of this class. It might happen on occasion if I'm making up problems like with weird numbers, if I just pick the numbers badly. Here we got lucky. So this was definitely an inelastic collision. Now, what if it was elastic? What would have happened to the same problem if I had known going in that the collision was going to be elastic? Well, when we started this problem, we would have had an extra constraint. We would have had an extra bit of information at our disposal. Specifically, we started this time out with these two equations. These two equations had to be true if I was going to conserve momentum. But in order to conserve energy also, I would have had a third equation. And that third equation would have been the kinetic energy before equals the kinetic energy after. So let's write that third equation. If going in, it was going to be elastic, I would have had the starting kinetic energy for ball 1, so 1/2 m1 v1 initial squared, plus the kinetic energy of ball 2 before the collision, but remember that was just 0, right? So all my starting kinetic energy is the starting kinetic energy of ball number 1, and then that would have to equal 1/2 times m1 times v1 final squared, plus 1/2 times m2 times v2 final squared. So these are the kinetic energies of the two balls after the crash. So if this had for sure been an elastic collision, we would have had to have had a different answer, because we would have had to have made these equations true at the same time that this equation was true. We would have had 3 equations. Now, check this out. If I'm just looking at this, one thing I notice is that in this equation, every term has a 1/2 in it. All those 1/2s, they cancel. Now, for this particular problem, all the masses were the same too, right? But if all the masses are the same, all the m's cancel. So what we would have ended up with, had it been an elastic collision, was that V1 initial squared had to equal V1 final squared plus V2 final squared. Now again, this is a very special case. It assumes that I have 2 objects, one of which was originally at rest, and both of which have the same mass. But if those 2 assumptions were correct, and it's elastic, that's going to be true. And if I think about this in just the right way, I see a really cool pattern. And here's the cool pattern. So V1 initial represents the starting velocity of the cue ball, right? The ball that was originally moving. And in my problem, that velocity was to the right? It was 8. So V1 initial is like an arrow that travels to the right, and it was 8 meters per second squared. Now, what's going to happen is V1 final, that's the final velocity of ball number 1. So the final velocity of ball number 1 was a diagonally down and to the right vector. So that's V1 final. Now, V2 final was a vector. And again, on my picture, it was a diagonally up and to the right vector. Now, in the previous problem, we were given what this is, but if I was going to have an elastic collision, V1 final would not be able to be the same as it was in the previous problem, and V2 final probably would be different as well. We don't know how big either of those 2 things have to be in order to be elastic, but here's a cool thing that I notice. If I take these 3 arrows and I kind of just shrink them all together, they're going to form a triangle where V1 initial is going to be the horizontal sideways part. V1 final is going to look down like this, and V2 final is going to look like this. But here's the thing, when I kind of just take these arrows and stick them together like a triangle, what I notice is that for this triangle, there's a relationship between the length of this arrow and the length of the other 2 arrows. This guy here squared equals this squared plus that squared. Wait a second. That looks familiar. Do you recognize it? I'm saying this side squared equals this side squared plus that side squared. What the heck am I looking at?
Pythagorean theorem.
It's the freaking Pythagorean theorem, right? So wait a second. For this very, very special case, where I have 2 objects who have the same mass, one of them is sitting there waiting to get hit, the other one comes in and hits it. This is very much like a pool ball problem. Apparently, the velocities before and after end up obeying the Pythagorean theorem. But the Pythagorean theorem only works for very special kinds of triangles, specifically right triangles, which tells me that this angle right here has to be a 90-degree angle. Now, notice that's the angle between the direction that object 2 goes flying off at and the direction that object 1 goes flying off at. So what's going to happen is, for this very special case, if I have an elastic collision between my 2 balls, they will always fly apart at a 90-degree angle. So what if I had gone back to the original problem and I'd said, hey, I need this guy to go shooting off at 5 meters per second, but now, or actually, I need this guy to go shooting off at a 45-degree angle, but I'm not sure how fast he's going to be going. So imagine I don't know that velocity there at all, but I know that when they collide, it's going to be a collision which is elastic. Well, what's going to happen is I'd have three equations, that equation, and this equation. I'd have three unknowns because I wouldn't know V1 final, I wouldn't know the angle, nor would I know V2 final. So three unknowns with three equations, still solvable. However, because of this little trick right here, I would know that V1 final and V2 final have to bounce away at 90-degree angles, which means if this was a 45-degree angle, this would also have to be a 45-degree angle so that this total angle would be 90. And that would allow me to solve my problem because now I would know these thetas and I could plug in and solve for V1 final, V2 final. I'd get a different answer, but I could utilize this energy conservation requirement to fill in one of my blanks for me. So it's a nifty little trick that you should probably remember, that if I have these two objects of equal mass bounce off of each other in this fashion, they will always fly apart at a 90-degree angle. So before we even did the math on the previous problem, because I knew that this angle was 45, the other was 38 something, I already knew the answer was going to be inelastic because I knew that in order for it to be inelastic, theta would have had to have been 45. And as it turns out, lo and behold, it certainly was. Does that make sense? You guys follow along with what's going on with this?
A little.
It just takes a little practice. The good news is this is as hard as it gets, right? All you really got to do is break things down in that same fashion. All right, how are we doing on time? All right, it's 12:24. Half an hour, can you do center mass in half an hour? Yeah, probably. So I'm going to show you guys something pretty cool. It's a little momentum simulation, which may or may not be something we do on Friday. I forget whether it's under M for momentum or C for collision. Maybe it's under neither of those things. Come on, man. Oh, there it is. Boom. Snakes, biting, etc. So this is a nifty little collision jobby. And what it allows me to do is to make little collisions occur. And you can see that you can do things in one dimension where, imagine here's my two objects. They start off with some velocity. And I had like a one-dimensional collision. You can see that the red guy has a mass of 0.5. The green guy has a mass of 1.5. And so what's going to happen is object one before the collision has a momentum of its mass, that's 0.5 times its starting velocity of 1. So it's got a momentum of 0.5. Meanwhile, this guy has a velocity of negative 0.5. He's traveling to the left at half speed. He's got a mass of 1.5. So 1.5 times 0.5 is 0.75. He's traveling to the left, so it's negative. So his starting momentum is negative 0.75. So how much total momentum do we have before the collision? Well, it's a one-dimensional collision, so the total momentum is going to be positive 0.5 plus negative 0.75, that's negative 0.25 is my total momentum. And when I allow them to crash, you'll notice they crash into each other. And after the collision, this guy is traveling to the left way faster than he was originally going. This guy's traveling to the right way slower than he was originally going. But if I look at the momentum before, I've got his momentum is negative 0.62. His momentum is positive 0.38. And what do I get when I add them together? What's my total momentum after? Oh, look, it's negative 0.25. It's the same after as it was before. So momentum was conserved, right? I could start that same scenario over again, only this time, instead of having it be elastic, I could have it be perfectly inelastic. When they hit, they stick together. And notice they're traveling at a speed of negative 0.12. They're to the left at that speed. But notice how much momentum we've got total. This guy has a momentum of negative 0.19. The other guy, who you can't quite see, has a momentum of negative 0.06 for a grand total of negative 0.25. The momentum is still the same. It's just now the kinetic energy is considerably less. So this is pretty nifty, but there's a concept that I want to explore, and it's a concept called the center of mass. And the center of mass is going to be useful in the next chapter because it's kind of like the average position of the mass in a problem. So let's hide that velocity vector for a second. If I have two objects, object 1 and object 2, and object 1 has a mass of 0.5 and object 2 has a mass of 1.5, where is the average position of the mass of those two objects? What does that even mean? Where would I expect to find that average position of the mass? Let's make it easier. Let's let their masses be both exactly the same. Where would I expect the position of the average position of the mass to be if this has got the same mass as this guy? Okay. Let's try another problem that maybe is more intuitive. Imagine that I'm going to change my grading scheme next semester. And you're only going to have 2 tests. Your entire grade is going to come from 2 exams. You come in on the first exam and get 100. And on the second exam, you get a 0. What grade are you going to get in the class?
Can you say that one more time?
Sure. Imagine that you've got your entire grade comes from 2 exams. They both count the same. You get 100 on exam 1. You get a 0 in exam 2. What grade are you going to get in that class?
B minus. Let's see.
No, you're not. How would you find your average if you had 2 exams, one was 100 and one was 0?
When you have to add them and divide them by 2, right?
Mm-hmm. Which would give you what?
So that's a 50.
Yeah, you get a 50. You'd fail that class, right? But wait a second. What's special about 50? Well, it's halfway between 0 and 100, right? So when you take an average of 2 things that both count equally, then what's going to happen is the average is going to be exactly halfway between them. So if I think of this idea of the center of mass as being conceptually like the average position of the mass, well, here I have some of mass over here on the right. I have an equal amount of mass over here on the left. So where is the average position? Right in the middle. And that's what I would expect if I calculate it. If the two masses are the same, the center of mass, the average position of the mass, is exactly in the middle. Now, what would happen if I go back and have ball 1 go back to being a smaller mass of like 0.5? Do I expect the center of mass to stay in the middle of the two objects?
No.
Okay. Where would I expect it to be if this was the case?
It would are you asking for one or two or both?
Well, I'm just saying, like, if I'm finding the average position for this scenario, where would I expect to find it? Just generally, not, you don't need to give me like an exact location.
Spaced out, I guess. Like,
So if it was in the middle, it'd be equally far from both of them, right?
mm-hmm.
Do I expect it to be equally far from both of them?
No.
Which should it be closer to?
It'd be closer to the two.
Yeah. Because the 2 is heavier, there's more mass over there. So I expect that my average would be closer to object 2 than it would be to object 1. And in fact, if I turn on the thing, that's definitely what happens. The fact that this guy has more mass means that my center of mass, my average position, is going to be closer to him than it is to him. As I change the relative sizes, you can see that it's getting closer to 1 the bigger I make it, and further from 1 the smaller I make it. And again, going back to the grade analogy, you see the same sort of behavior there as well. Imagine that your grade in my class came from 2 assignments. One is the final exam, which is 80% of your final grade, and one is another quiz that's only worth 20% of your final grade. If you get 100 on the final, but only a 0 on the other quiz, then obviously your grade in the class is going to be between the 100 and 0, but it's going to be closer to 100 than it is to 0, because the final exam counts a lot more. If you flipped it the other way around, you'd be in trouble, because if you had 100 on the quiz but a 0 on the final exam, your final score for the class would be a lot closer to 0 than it would be to the 100 you got on the quiz. So essentially what happens is, when we talk about this center of mass, it's going to end up being important because it's like the average position of all the mass in your problem. And because different parts of an object might have more mass than others, that might determine where your center of mass is. So here's why I might care. So I got this pen, right? And we've learned how to do forces, and we know that if gravity is pulling this pen down with a force of its mass times g, but if I push up with a force equal to its mass times g, I should be able to cancel that out and cause the object to sit still. However, it's more complicated than that, because if I just put my finger right here and I try to hold the pen up by pushing upward with the same force as gravity pulls down, it's not working. It keeps falling off my finger. Why is that? Because every time I put it on my finger and I let go, it rotates around and falls down. So what's going to happen is, when it comes to rotational motion, I got to worry not just about how hard I push, but also where I push. However, if I play around with it just enough, if I'm lucky, usually in class I do this with a ruler, which is easier. If I do it just right, I found this one spot on the pen where if I push on that pen at that one spot upward with a force equal to gravity, I can keep the pen from falling. It's not rotating, it's stationary. Now, it turns out that, as we'll see in chapter 9, the location where I'm pushing it is at the center of mass of the pen, the average position of the pen. However, because one half of the pen is a little bit heavier than the other half of the pen, notice I'm not exactly in the center. I'm a little bit closer to the cap than I am to the tail, because there's a bit more mass at this end than there is at this end, right? If the mass were evenly distributed, I would be exactly in the center of the pen, but I'm a little tiny bit off center because of that. Does that make sense? So this concept of center of mass gets introduced during the momentum chapter, and it has some implications for momentum, but it's going to also be important in the next chapter where we talk about rotation, and we start to worry about where forces act on an object. That's what we're doing with this. So we're going to need to figure out how to find the center of mass of a system or an object, and it's super easy to do. So it's going to be an average, but it's got to be a weighted average. It's got to be an average for which the more mass you have, the more you're going to contribute to that average, so that things that are more massive are going to count more than things that are less massive. And the way we'll do this is we'll say that the position of the center of mass is going to be the position of the first piece of mass times the mass of the first piece of mass plus the position of the next piece of mass times the mass of that piece of mass, plus, if I had additionals, I could keep doing this for all day long. But then we're going to divide this, because remember, this has units of position, so meters. This has units of position times mass, and I can't do that. I have to have my units be the same on both sides. So I have to divide by a mass, but I'll divide by the total mass of everything. So now the kilograms over kilograms cancels, and all of this is going to give me some distance. And to see that this is going to work, to find the center of mass the same way that the simulation was doing it for us, let's start with the one that's it's easy to know the answer. So here's M1, which is, let's say, 1 kilogram. And here's mass 2, which is also 1 kilogram. And let's set them a distance of 3 meters apart. Now, I already know the answer to this. I know where the center of mass has to be. It's going to have to be right there in the center, right? Because the two masses are the same. And I just want to verify that this formula works as intended. So how will I play this out? How will I find the position of the center of mass? Well, first, I'm going to choose a coordinate system. And as always, it doesn't matter where I choose my coordinates. So I'm going to go ahead and call this x equals 0. That, of course, implies that this is x equals 3 meters. And so when I go to find the position of the center of mass, it'll be the position of mass 1, which is 0. So 0 times mass 1, which is 1 kilogram, plus the position of mass 2, which is 3, times mass 1, which is 1, over the total mass of everything, which is 1 plus 1. Oh, look, that's 0. 3 times 1 is 3. 3 divided by 2 is 1.5 meters. And oh, wait, where is x equals 1.5? Well, if this is 0, 1.5 is right there in the center. So this formula gives me the answer that I expect in the obvious case. But what happens if mass 2 is way heavier? How does it change my answer? Well, position 1 hasn't changed. So that first term is still going to be 0. But now it's going to be 3 kilograms times 3 meters. over the total mass. But now the total mass is 1 plus 3, that's 4. .25 meters. Well, if this is x equals 0, 2.25 is going to be more than halfway. And so it's going to be way closer to this guy and further away from that guy. And that is exactly what we were seeing in the simulation. So what this method of averaging does is it helps us find sort of an average position of all the mass in my system. And the reason this shows up in my momentum conservation chapter is because of the following. Let's go back to that simulation for a second. And what I want to do is I want to look at the center of mass throughout this collision. So let's start off with, I'm going to back these guys up. Let's give this guy velocity. Let's give this guy a little velocity. And I don't want you to watch the two balls. What I want you to watch is that little black or that little yellow X. And I want you to watch to see how the motion of that little yellow X changes at the moment these two things collide. All right? So don't pay attention to the balls, pay attention to the X and watch what happens. So when those two balls collided, what happened to the motion of that X? How did that X motion change? Let's try it again. Let's make it more exaggerated. Let's have these guys travel and hit each other way faster. Again, watch the X. How did the motion of that center of mass change when those things collided? How about now? This one hopefully should make it super obvious. Super obvious. So, two balls, equal mass, both coming at each other at the same speed. How did the motion of the center of mass change when those two things collided? Well, Tom, nothing changed at all. They did nothing. All right. So what's happening in this situation is that the motion of the center of mass of the particles did not change one lick during that collision. And that's awesome. It's actually a consequence of momentum conservation. If I have a closed system and I calculate the center of mass of that system, those objects can bounce against each other any way they want, and it will never change the velocity of the center of mass. Whatever velocity the center of mass had before, it's going to be the same after. And so you see that even in really complicated situations, like here's a two-dimensional system. And again, I'm going to do the show values. I'm going to turn off the border. When I crank their masses down so that they're the same, and here's my center of mass, like right there in the middle. And I'm going to have them hit each other in a glancing blow. And notice that that center of mass didn't move even a bit when they collided. The center of mass had the same location every time. Now, here, when I have these guys collide, the center of mass is probably going to be moving some. So it's going to have some velocity. But notice, even as they, oops, I missed. That was embarrassing. Come on. There we go. Return balls. All right. So notice the two balls drastically changed direction, but the motion of that center of mass did not once change the entire time. And that's helpful to us. That tells us a lot of stuff. For one thing, if I know the position of the center of mass or the velocity of the center of mass, and something goes and happens that maybe causes the constituent parts of my system to change direction, I can often use that center of mass velocity as a basis for figuring out where the other pieces of my object land. Imagine I have the following scenario. So imagine that it's 4th of July and I take, I don't know, like a M80 or a black cat or something, and I throw it into the air. And I throw it with some initial velocity of, let's say, 10 meters per second. And I throw it at an angle of 60 degrees. And what's going to happen is it's going to fly up into the air. And then at the top of its arc, it's going to explode. And what's going to happen is, let's, for simplicity's sake, say that it explodes into two pieces. One piece goes flying this direction, and the other piece goes flying off that direction. Or, heck, let's make it three pieces. And so what's going to happen is these pieces here, after the explosion, land in some location. But I'd like to find this piece right here. I'm not sure where it landed. Well, what's going to happen is the center of mass of this system will not be affected at all by the motion of my particles, which means the center of mass of my system is going to have to be the same before and after the collision. So here's what I could do to solve this problem. Right? So what I can do is I can treat this as one big firecracker, and I can figure out, if I have that one big firecracker, where would that big firecracker have landed if it never exploded? Well, that's a chapter 4 problem. So this is where an unexploded firecracker would land. All right. If I find 2 out of the 3 pieces, they're going to probably land in a different location than where it would have landed without the explosion. Maybe this piece over here went a little bit further. Maybe this little piece over here landed back over here somewhere. However, what's going to happen is the velocity of the center of mass would have been exactly the same before and after the explosion, because all the forces of that explosion are internal forces. They can affect the momentum of individual particles, but not the particles as a whole. So if I figure out where that location would have been, and I can do that easily enough, because if we ignore the height that I threw it from, we can use the range equation. To figure out where this guy would have landed. So that's going to be 10 squared over 9.8 times the sine of 120. So I expected that that firecracker would have landed 8.83, not meters, meters from me. Had it not exploded. Oops, sorry, that's distance. So that's where I expect the center of mass ought to be, at that location. Now, let's imagine that this firecracker only landed from me a distance of 3 meters. It was way closer than I expected. And this piece of the firecracker ended up way further, let's say 13 meters. Where's that third piece going to be? Well, for that, I can go back to my center of mass expression. And I know that the center of mass has to equal x1 m1 plus x2 m2 plus x3 m3 over m1 plus m2 plus m3. And the position of the center of mass has to be 8.83 meters away from me. So this is known. Let's assume that the masses break down like as follows. Let's say that the whole firecracker is, let's say, I don't know, 50 grams. However, piece number 1 is 10 grams. Piece number 2 is 15 grams. And that implies that piece number 3 has to be the remaining 25 grams. Right? So they all add up to 50. Now, if that's the case, I'm solving. I've got 8.83. I got position 1, which was given to be 3 meters, times mass 1. I'm going to leave this in grams, which is fine as long as I get my, I'll get my answer in whatever units I put in. X2 is going to be position 2, which we said was 13 meters, times mass 2, which is 15 grams, plus X3, that's the position of the missing piece that I don't know about yet, times 25 grams, all over the total mass, which was 50. And all I've got to do is get X by itself. So I'll multiply both sides by 50. Three times 10 is 30. 13 times 15 is, I don't want to do it in my head. 195. So when I move this over and multiply this out, I get that's going to be 216.5 equals 25 x3. Again, I just multiplied this out. I subtracted 30. I subtracted 195. I got this divided by 25. So apparently the third piece must have landed 8.66 meters from me. So where did the third piece landed? It actually landed right there. How can I deduce that? Well, I knew where all the other pieces landed, and I knew that the velocity of the center of mass could not have changed. And since I knew where the center of mass would have landed, I could then deduce where everything else landed as well. Now, if you guys remember back in the day, the space shuttle Columbia exploded on reentry. If you recall, what happened was when it took off from Florida, there was a piece of foam insulation that broke loose. It broke a hole in the wing, and it got into space just fine, but they weren't able to repair the hole. And so when they came back down, they're traveling at like 17,000 miles per hour, exceptionally fast. They hit the atmosphere, and suddenly you're getting lots of frictional heating from the atmosphere upon reentry, and that causes lots of heat. Gas seeps into that hole, gets into the orbiter, causes things to explode, and it explodes, and it ends up spraying debris across 5 states. Crazy. However, they were able to find virtually all the pieces of the orbiter. Why? Well, because once you find some of the pieces, and it's kind of obvious when a big flaming ball of metal falls out of the sky where it landed, but once you know where those pieces are, you could figure out, you know, those locations. You knew where the orbiter would have landed because we have from telemetry what speed it was going the moment that it was first crashed. So we know where the orbiter would have landed if there had been no explosion. And so once you find several of the pieces, the location of the center of mass tells you where to look for the other pieces. And we were able to recover almost all the pieces of that orbiter in that disaster. So super fun, super easy. We'll talk next time about how to find the center of mass of not just a set of objects, but a singular object of irregular shape. We can only do so much of that because for objects that have mass that is distributed unevenly, in order to do a really exact accounting, we have to use some calculus, which we can't do in this class. We're not a calculus-based class. But for some objects that have nice regular shapes, we can sometimes avoid the calculus just by using a bit of common sense. And so that's what we'll be doing tomorrow. Any questions about what we did today?
No, not right now.
Okay. Well, in that case, I will see you guys tomorrow. Have a good day.
Thank you.
Thank you.
You're welcome.